Okay, so we have a block over here that has a mass of 10 kilograms and is compressed 15 centimeters of this spring using a force of 588 newtons, and then it's released and goes up this ramp of 37 degrees. Alright, so we can basically divide this motion into three parts, A, B, and C. We use C as the initial part, and A as the part at which the spring is fully compressed, and B at the part at which the block gets to a stop while being pushed, although we are going to get to another part in a while. So for our first part of the problem, we are asked how much distance does the block cover until it stops moving. So we can simply use conservation of energy between part A, which is the part at which the block is compressed, and part B, which is the part at which the block stops moving. So in order to do this, we know that at part A we don't have any height, so we don't have any potential energy, and we don't have any kinetic energy because the block isn't moving. So the only energy we have is the potential energy of the spring. But we are missing a constant here, which we can calculate because we have a force over here and we have a distance. So by knowing that the force equals 1/2 of kx squared, we can simply work it out of here, and we get that 588 newtons divided by 0.0025, which is 2 times the distance that it is pushed, equals 23,520. So this is our constant, which we are going to substitute when we use our calculator to use this. So here it's pretty simple. We only have this equals this, and we need to work out L, which is the distance at which the block stops. So we get that L equals kx squared divided by 2 times mg sine of the angle. Alright? So by putting this in our calculator over here and using this data, we get that the distance that it gets to move before it gets to a stop equals 4.48 meters. So in the part B, it asks us, when the block has moved 3 meters upwards, which speed does it have? Because it has obviously not stopped, because it stops until 4.48. So by doing this, we can simply know, like, 3 meters over here has also a component over here which we can calculate for the potential energy with trigonometry, and we get that this movement is going to be between A and this point over here, which isn't neither A, B, or C. It's another point which is 3 meters up the ramp. So here we got that at the point A we have the same as over here, and then at point 3 meters we have a potential and a kinetic energy because it has already acquired height and motion. So we know that is the potential energy equals mass times the gravity times the height, which is 3 times the sine of the angle because it's the opposite side. And then we simply have plus 1/2 of the block's mass times the velocity, which is the one that we want. So all we have to do over here is work out the velocity, and we have that kx squared divided by 2 equals, subtracting mg3 sine of the angle, all this multiplied by 2 and divided by the mass with a square root will give us a speed of 4.19 meters per second. So that is part A and B. Okay, so for part C of the problem, we are given a coefficient of kinetic friction of 0.20, and we're asked to do the procedure all over again. So what changes here? Practically, we have a work that the friction is doing on the block that is opposing to the motion, which we are going to add in the second part, because in the first part the block isn't moving and therefore there isn't a work of kinetic friction or any kinetic friction energy. So we simply add here the force of kinetic friction times the normal, and we know that Fk equals mu k n, and this normal force we can calculate by doing the free body diagram of this block and getting the weights component in the respective field. So what we need to do here is factor out the distance, which is also here because we're doing work and energy. We get L times mg sine of the angle plus Fk, which we already can calculate because we have over here, and then 1/2 of kx squared. The constant stays the same and the distance stays the same in this case. So practically all we have to do here is work this one out by getting these two dividing over here, and we will get a final L of 3.54 meters. That, compared to the 4 meters and something that we got before, is less, of course, because the friction is subtracting some energy. And then we need to do it for the 3 meters. So we have this equation here in which we have a kinetic energy, and we simply need to add here FKL, and in this case L is going to be different. L is going to be 3 meters, and that's practically it. We can factor it out again, and we can work the velocity out of here, which will give us, by plugging into our calculator, a velocity of 2.85 meters per second. That's it.